Welcome back. What we are starting today is a discussion of balanced trees. The first exam material ended with the idea of binary search trees, which were trees in which we had an ordering principle involved, and we were able to search the tree in such a way that we only had to search down one particular path. And we had mentioned that one of the problems with this idea, the idea of basing a binary search tree or basing our searches on that kind of a tree, is that even though in the average case we had a roughly balanced tree, some picture like this for example, and we get on the order of log n for the height, and since the operations were based on the height, then we would expect to order log n time for the operations as well, insert and find and remove. We said in the worst case you could have a tree that looked like that, where it had all left children or alternatively all right children. And so it was effectively just a linked list that we are calling a tree because there were extra null pointers. And so in that case, the height of the tree is linear, it's order n. And so the operations, which are based on the height of the tree, would be order n. So the operations are always based on the height, it's just a matter of what the height is. So if there was some way of enforcing the top situation, enforcing the idea of this tree being closer to having relatively equal subtrees rather than having a list-like structure, then we could guarantee log n time for these operations, or at least for the binary search tree part of them. And that's going to be the goal we shoot for here when we talk about an AVL tree. And we're going to get into exactly what balanced means, but essentially it's going to be a binary search tree that is balanced. And so that roughly is going to mean that the height, or the consequence will be that the height of tree is order log n. We're going to talk about exactly what the definition of balanced will be, but our consequence will be that the height of the tree is log n, and so therefore we will have both the average and worst case e log n for the operations. And that will be the idea here. We eliminate the linear time worst case of a binary search tree by ensuring the tree does not have these long linear chains in them, but that instead you have this balanced structure to them as in the top picture here. And so if you can, though we're going to in a moment, I guess I said, precisely discuss the definition, if your tree is more or less arranged in that way, then as you start to search the tree, every decision eliminates about half the nodes remaining, because you've got about equal numbers on both sides of a node. So if you choose to go to the left subtree of a node rather than the right subtree, then the right subtree nodes that you never have to look at, that is about half of the nodes that you have total, and the left subtree would contain the other half. And so the idea then is if at a given node, the nodes in its subtree, there's half of them on each side, half of them in its left subtree and half in its right subtree, then making a decision that will eliminate half the nodes because you won't have to search that side. And so the goal here is to try and set things up so the tree is more or less like that all over the place rather than being in this form down here. So given that, we then need to talk about exactly what definition we might use for this procedure. And one possibility, as far as the definition goes, is to focus on the size of the subtrees. Because after all, if we're going to focus on these, if we're going to talk about how to ensure that we eliminate exactly half the values in each step, well, then that would be one way to do that, is to say that we make sure that there are exactly half the values in each step, or half the values eliminated in each node. And that is to say here, we could describe our balance as being some description like at every node, subtrees are of equal size. So we have a situation like this, where we have here, say, k nodes here and k nodes here. And then this is order log n. And then within these subtrees, the same thing would apply. The root of one of these subtrees would have, some certain number of nodes in its left subtree, and it would have the same number of nodes in its right subtree as well. So that's one way of defining balance, to simply say that that has to be the case at every node. And there's actually that actually is completely impossible to achieve in general. And if you want, you can pause the tape for a moment and think about it. There's a subtle flaw here that makes that impossible to achieve. And I'll pause for a moment while you give that some thought. Okay. So if you're looking at this now, one thing that might spring to mind is, what happens if I have 4 nodes? One of them could be the root, and now I have 3 nodes to distribute across 2 subtrees, and that is not possible if I want to have both subtrees have the same number of nodes. So there's this subtle issue where, okay, you can't quite do that if you have an even number of nodes. Then you have this issue where, you know, in this case, if you have k there and k here, this is going to be 2k plus 1 nodes total, and that is not even. So technically we can't make this work without adding sort of a addition to it. Add an addendum. Subtrees are of equal size or differ in size by 1. It's sort of, I don't want to say a trivial point, it's a minor point. But it does illustrate, I think, the importance of making sure you think things carefully through, because even things that seem like certainly impossible to achieve can have these very slight difficulties with them. And so we can then look at this and say, well, now will this work? Now that we've made it workable, we said, okay, now that'll work for even number of nodes as well as odd number of nodes. Now does this definition work? And here the answer is, well, yes, it works. But the question then, the second question that comes up is it restrictive? Is it too restrictive? Certainly, if we have a near balancing like that among the subtrees, then you're eliminating half the nodes at each step, and that's the definition of logarithm, basically. And so you'll have an order log n height tree. But in addition to worrying about whether this will work or not, the question is it too restrictive? And you ask, how can it be too restrictive? You know, it gets us what we want, the log n height. What's the problem? And the problem is trying to maintain this property could be very, very, very expensive. So for example, let's consider here a tree looks like this. Say we have k nodes here and k plus 1 nodes here. And now we do some sort of insert, and it's going to be some variant of a binary search tree. We said the goal here is to balance a binary search tree. So inserting a node that's larger than everything else in the entire tree would end up inserting here, or somewhere like that. I would become the rightmost element. So if the tree contained all integers or integers that are all in the range 1 to 100, and then you insert 115, well, that certainly would be the very rightmost element in the tree, because it would be the maximum element. And so the question is now, what happens here? Without really knowing any of the details about how we might go about fixing it, we do have some idea of what would need to happen. Because now we've got k plus 2 nodes on the right subtree and only k nodes in the left subtree, and we said they had to be equal in size or differ by 1. They originally differed by 1, now they differ by 2. So we need to fix that. And there's really only going to be certain ways in which that can be fixed. What we will need to have, well, we have here k plus 2 nodes, and we have here k nodes, and we have here 1 node. That adds up to 2k plus 3 nodes, and the only way to balance this out then is to have things set up that we have k plus 1 nodes in each subtree. So we eventually need to go from the top picture to the bottom one. We need to say, well, I've got 1 too many nodes on the right side. I need to somehow get some node over to the left side. And then that will balance out the subtree sizes again. And you think, well, okay, that seems easy enough, except that we've got the binary search tree ordering principle to worry about. I can't just pull some node from here and stick it there, because anything greater than a root needs to remain on the right side of the root. So if I want k plus 1 elements in the left subtree, those k plus 1 elements need to be those elements. The k elements in the left subtree and also the root. And the new node in between them needs to be the minimum node in that subtree, because now we'll say these k plus 1 elements are in the left subtree, you have k plus 2 elements in the right subtree, and that set of k plus 2 elements could be broken up into the very leftmost element, the minimum element in the right subtree, the one I've circled here, and then the other k plus 1 of those k plus 2 elements. And so moving this up to here, this would be the new root, and then this would be the other k plus 1 elements. So that's how this would have to be arranged. You have to say this collection forms the left subtree. You have to take what it essentially amounts to, the in-order successor of the whole tree's root, and that becomes the new root. And then the remainder of these become the right subtree. And certainly, you've got some finagling to do right off the bat as far as arranging this, because you've now got to move the root into here. You know, put the root's got to be here, and you've got to move this one up here. So you can already see there's some manipulation to do. In addition, you've got to look at both subtrees, because now if we've got some new nodes sticking there, and we've pulled off the value there, though we haven't looked at the details of that tree, they could be affected. We might have to go through and somehow rearrange the nodes of that tree to have this strict balance in place. And likewise here, just having a tree with only a left subtree and no right subtree isn't going to do any good. So this node needs to be inserted into here somewhere to balance out the resultant subtree. And so we need to worry about that as well. So not only have we had to sort of rearrange things at the top level, but both subtrees potentially need to be messed with now. And so when you mess with them, then you might have to mess with their subtrees and further on. You might potentially, you know, in a very bad case, potentially look at every node in the entire tree when you do this. And that can be very expensive. The idea here being, if you need to absolutely hold on to the idea of the subtrees remaining nearly equal in size, it'll be so restrictive that to maintain that property, it's an excellent property for achieving balance, but to maintain that property will be just too expensive. It'll be so expensive to maintain that we won't get any gains from keeping things log n in the first place. If the height's log n, sure, the insertion itself, it would have been log n to get this value inserted into there. And then rearranging the tree to maintain the whole balance principle all over the place is just going to chew up all the time we saved. So instead, perhaps there's a somewhat less restrictive definition that we could make use of that would still be something that we can that works for us, but is not quite so expensive to maintain. And in fact, there is such a definition. And the idea here is going to be that we will say, well, it's not really the sizes that we're worried about here. If we're worried about the tree being logarithmic height, there are a number of trees that could be, you know, say height 4, that aren't all going to be exactly the same size, but they'll be height 4. You know, so you might have a tree that looks like this. And so here's a height 2 tree. There's more or less a kind of a balance going on there. And you think, well, I could have added nodes to this right side as well, and that could be a height 4 tree as well. So I could have then proceeded to say, well, take that same tree, take a similar tree, and I could have had other nodes here too. I could have had this one and this one and this one, and maybe one here, something like that. So there's clearly more nodes in the right-hand subtree, and yet it's the same height. And so if we have two subtrees that are the same height, neither of them is going to, you know, the tree that this whole subtree would be a part of would be the same height if we replace this with this, or vice versa. The idea being that we're not really concerned with the size so much as the height of our trees. We want to make sure that we don't have a particular tree becoming too large in height, and that was the problem with the binary search tree worst case. Since we always had everything on the left, the left subtree of the row was very, very long, and the right subtree didn't exist. It was null, basically. So let's have a definition based on the height instead, and say that our balance, or we'll call a tree balanced, if at every node subtree heights differ by at most 1. We could say subtree heights will be exactly equal, and we will proceed to run into the same problem we ran into with the size issue. Well, if you have two subtrees that are exactly equal in height, and then you have one insertion that would extend the height of one of those trees, it's like, well, how do you work that in? You can play around with that yourself if you want. I'm just going to cut to the chase and say you'll run into that same trouble, so we need to not say the subtree heights have to be equal. We'll allow them to differ by at most 1, just like we did with the size. And that way we've got a little bit more flexibility there for particular insertions. And so this turns out to work. I'm not going to go over the proof, but it is in your blue textbook, assuming you've got blue textbooks. It's not important for this class. What's important is that we cut to the chase, or the result here that we'll cut to the chase with. If you have that property, it can be proven the height is going to be log n. And I think specifically it turns out to be about less than or equal to 1.44 log n is, I believe, the proof result. So your height will, in fact, be no greater than some constant times log n. And so as a result, this definition will work for us. Like I said, we don't need to worry about exactly how that is proven, though certainly I would encourage you to look at the proof or find it in the book. The idea then here is you have trees such as this one, where we say here, we got a tree here, some nodes here, and then something here, and let's throw in here. And we will consider that to be a balanced tree. The height of the subtrees differs in a few places, but we're okay here. And if we were to kind of look at the individual heights, I'll write the heights to the right of the node traditionally. We can say here the height is 0. That height is 1. All the heights of leaves are always 0. And so you start there. And then you can say, well, how exactly do you calculate the heights? And we can say, well, the height of a node is equal to the maximum of the height of subtrees, of its subtrees, plus 1. And so the idea here is then that when you look at the two subtrees, you say, well, what are the two heights of the subtrees? And you add 1 to them. Just like at the root node here, we'd say, what's the height of this whole tree? What's the height of this whole tree? And whichever one is the maximum, that contains the deepest path to a leaf. So we're saying if I want to find the tree, go down to the deepest possible leaf, my two subtrees, when I have those, the one of greater height has the deepest leaf. And so I would essentially be picking this one, and then I'd say add 1 more for the connection to the root. And so that's where we get that formula. The two subtrees, whichever one has a greater height on its own, is the one that's got the deeper leaves, and that would be how I establish my own height, is by saying the path to my lowest leaf. And so picking the maximum of the subtrees picks the proper tree in that respect, and then we have the plus 1 because there's one extra edge from the root of the subtree to the root of the actual node itself. Note here that if we're going to make this work, we need some kind of a definition for null subtrees, such as this one. And so in that respect, then, we can say, well, if we're going to have a pattern here where we can say something like that is of height 1, and that node is of height 0, when you have two null pointers, well, then following the pattern, this should be of height -1. Sort of a little null subtree should be of height -1. And that's what we'll do. We'll say that null subtrees are of height -1 to keep a pattern with the idea of a subtree of just one node being 0, and then if you add a child to it, you have 1, and if you add a child to it, you'd have 2. So working in reverse, these will be -1, and therefore here we say, and that's the way leaves work essentially, because you have two different subtrees, both height -1, both they don't exist. And so the maximum of that is -1 plus 1 is 0, and that gives you the height for a leaf being 0. So that's going to be our standard definition of the height, just to make the math work, the height of a null subtree, which is different than the height of a one-node subtree, so be careful with that. A leaf has height 0. And therefore, this has height 1 because you're the maximum of 0 and -1 plus 1. This has height 2, the maximum of 0 and 1 plus 1. That's height 1, that's height 2, that's height 3, and that's height 4. So those are the heights if you want to record that, and you can look at every single node. To take the root, for example, the difference between 3 and 2 is 1. And so that works just fine as far as our definition goes. And in fact, at every node in that tree, the subtrees differ by at most 1. So we're okay there. We also can have the definition of balance because we want to talk about whether things kind of skew to the right or left here. So we can say the balance of a node will equal right subtree height minus left subtree height. We could have defined it the other way too, but this is the definition in the book. Balance is right height of a subtree minus the left subtree's height. So for example, leaves will always have 0 balance because their two subtrees are both -1 in height. Neither subtree exists for this node, so they're equal. The balance then becomes 0. And I will traditionally write the balance on the left of the node in my examples. So for all leaves, since you have 2 null subtrees, the balance is 0. And then as you start to look at the other nodes, basically you're saying, for example, here, for this node, to give an example, the balance here is negative, or the height here is -1, the height here is 0, the balance therefore is -1 minus 0 is -1. For this node, its right subtree has height 1, the left subtree has height 0, the balance here is +1. And you can see that by virtue of the right subtree being 1 larger than the left. The balance here is -1. For that node, the right subtree has height 1, the left subtree has height 2, so right minus left is -1. The balance here is -1, the balance here is -1, and the balance here is -1. All the leaves have balance 0. Some of the other subtrees could have balance 0 too, but they don't here. In this case, all our non-leaf nodes happen to have and this one's +1 here. In our picture here, all the non-leaves happen to have a non-zero balance. That wouldn't always be the case. But the idea is, for example, here we say for this node, the height of 2, the right subtree has height 0, the left subtree has height 1, 0 minus 1 is -1, that's where we get that. So it'll be 0 if the two subtrees are of equal height, it'll be +1 if the right subtree has a greater height, and it'll be -1 if the left subtree has a greater height, as with our root here. The left subtree is height 3, the right is height 2. So when the left subtree is larger, then the balance is negative. And then we'll use that basically to determine, as we talk about various situations we run into. So those are sort of our establishing definitions here. The idea of how to calculate the height, how to calculate the balance, and what those both mean. And so we're going to be making extensive use of all those. So we need to get into here now the issue of how to fix this work, how to do the binary search tree work. And the thing to mention is that the work can't take an infinite amount of time. We're constrained in a certain manner. Firstly, the question is which operations will need to be changed. And I'll give you a moment to think about that if you want to pause. Okay. The idea should be that any operation that can actually mess around with the tree heights should be changed. So find, for example, doesn't need to change because all it does is search the tree. If you have a log n height tree to start with, find is going to search the tree. It's still log n at the end. However, insert and remove both need to be changed from the binary search tree version. Something occurred to me, maybe my question before the tape pause wasn't entirely clear. So if you had no idea what I was talking about, I apologize. The idea of here, insert and remove, both of those could potentially affect the height of subtrees as you insert new nodes or remove nodes, and that could result in our trees being in error. So we will need to write new versions of those, and those new versions will start out with a binary search tree operation and then do any rebalancing work that needs to be done. And we know that this will be ordered log n because we say we have an AVL tree, the height starts out at log n, and so since the binary search tree part of the operation is based on the height, we know it won't take any longer than log n time. The question is, how long should that rebalancing work take? And, well, when you think about it, if you have here order log n for the BST op, and if you had then order n for the rebalance work, I just say re-B work, then that's going to equal order n time. That is, if the rebalancing work is more than log n time, the rebalancing work will be the dominant part of the operation. If we want things to stay at log n time, well, we're okay as far as the binary search tree part goes. But we can't have the rebalancing work take any longer than log n time either. So in other words, this is the critical part here. The rebalancing work can't take any longer than log n time, because if it does, then the whole operation will take longer than log n time. But if both of these are log n time or better, then when we add them together, the entire time to run the insert or removal would be log n time as well. Log n plus log n is log n, just with a slightly higher constant. So that's, as we look at this, the whole key here is going to be that we can't have rebalancing work that takes longer than log n time. Because if we do, we're going to be stuck in the sense that the rebalancing work will dominate the operation. It'll be more extensive than log n time. So, as a result now, we need to start talking about how to fix this. And we're going to be talking about the idea of rotations. Rotations are going to be what repairs our tree. And we have, of course, you don't have any idea what these are yet because we haven't talked about them. What I want to do first is give you this sort of broad outline overview of where we're going with this. And so we will say first that the rotation, the first thing we need to learn is, or the first thing that comes into play when we start dealing with AVL tree operations, is where to apply the rotation. Second, we will be concerned with, okay, once we've decided where to apply the rotation, which rotation to apply. And third, once we've decided where to apply a rotation, we know at what node in the tree, and which rotation to apply, then we say, okay, now I know where I want to do this operation and which operation I want to do. The question now becomes, how do I do it? And so that's what we're going to actually look at first, just so you have some idea of what we're talking about when we mean rotations. That's the idea here. So the rebalancing work that we have to do is going to depend on these rotations. And we're going to, by the end of the rotation discussion, you'll have a pretty good idea of exactly how we're supposed to do all these kind of things. But the idea will be that the total time we spend doing these rotations and figuring out where to do them and so on and so forth won't total more than log n time. And that way, as we said in the previous slide, the rebalancing work doesn't take more than log n time and we'll be all set. But this is the outline you want to keep in mind. Basically, as we start to do the rebalancing work, the AVL tree operation seems very complicated at first, and you'll see over the next few lectures that it seems kind of complicated. It's something that you need to practice with. But inevitably, as you start to practice with it, things will become easier. The AVL tree problem on the exam, when we've had it one in the past, has almost always been gotten, just about, correct by just about everyone. So don't panic as you start to think this is kind of confusing. This is probably one of the hardest topics of the course to learn, but it's also one that once you learn it, once it clicks into place, you're okay. So you just have to kind of familiarize yourself with the patterns that we'll be dealing with, and generally everyone has an okay time with that. So don't worry too much about this. Just kind of think about it a bit and let it settle in as we talk about things. But this is the outline to keep in mind. The idea will be, as we start to talk about various topics, you're going to fit them into this outline, thinking of, okay, now this is talking about how to do the rotation, and then later on, where we apply it, and so on and so forth. Ultimately, what will happen then is your insert or remove for an AVL tree will be do the binary search tree operation, which you already know, and then run through this step. Figure out where to apply your rotations, figure out which ones you apply in those positions, and then you know how to do them, you go ahead and do them, and that'll fix the tree. And that's all there is to it. Binary search tree operation, and then figure out where you do your rotations, figure out which rotations to do at those spots, do the rotations at those spots. You'll be all done. So that's sort of the high-level summary of how to fix an AVL tree. What we need to talk about now is exactly what rotations are and how to go about dealing with them. So, we have two types of rotations, a single and a double. That's one way of putting it. We can also say that we have two types of rotations, right and left. Therefore, in reality, we have four total rotations. We have a single right, which I'm going to abbreviate SR. We have a single left, which I will abbreviate SL. We have a double right, which DR, and then double left would be DL. And those are our rotation types. We're going to look at all those, but basically they're not, you don't really have to learn four different operations. There's a huge amount of similarity between these. But the idea will be that there's four distinct operations, each considered a rotation in its own right. So you have four operations. You'll have to decide which one is appropriate in any given situation, but the idea will be that to fix a node that's out of balance, you will either do a single left or a single right or a double right or a double left, and that will repair that node. We're going to look at the single right today. The single left is going to be easy to remember once you've done that, because the single left is simply going to be the mirror image of the single right. When we look at the single right, every time we would say right, you'd say left and vice versa, as we manipulate pointers and such. So once you know the single right, you basically know the single left too, because you flip the operation around. And then when we look at the double right, there are a number of ways you might remember the double right. I happen to think the easiest way to remember this is to think that it's made up of a single left and a single right. And we'll talk more about that in detail when we talk about double rotations in the next lecture. But the idea will essentially be that though it counts as one operation, a double rotation is one operation, one easy way to remember how it's done is that it's sort of a composite of two single rotations. That doesn't mean we should count it as two rotations. It's one rotation. It's a double rotation, one operation. But it's composed of basically two singles. And so we can look at that and in detail. And so then the double left will be basically the mirror image of the double right. So given those facts, there's not really a whole lot you'll have to remember. You'll have to know the single right rotation that we'll look at today. That gives you the single left as well. And then you just have to remember the double right is made exactly how we combine two single rotations to make up the double. And so I sort of think of it as remembering 1.5 rotations. You need to know the single right, and you need to know exactly how two different single rotations would be combined to form the double. You'll understand how to do those rotations already. It's the combination, how to tie them in together, that you'll need to understand. So you're sort of, once you learn the single right and then the single left, you're halfway towards understanding the double right. Then it's how they're combined together that is what matters. And then the double left and single left you just get as mirror images of the right ones. So it's not really 4 rotations you have to learn. I would more describe it in the sense of saying you're learning 1.5 rotations or 1.5 collections of information. So given that, let's look at the single right first, because we've talked very vaguely about this long enough. It's time to actually get into some details. So let's imagine a situation where we have a tree like this. And I say I have here a pointer to here. Let's say this holds the value K2, and we have here the value K1, and a subtree A of height H, and a subtree B of height H, and here we have a subtree C of height H. Now you might ask what happens if those heights aren't H. Don't worry about it. Eventually you'll understand that situation as well. I have to pick some example to do, though. I'm picking an example where all 3 subtrees have to start at the same height here. A, B, and C are meant here to describe subtrees that are perfectly legal. So we're saying, and you'll understand this more later on as well, but we're saying for the moment we don't care about the details of A, B, and C. We know, and you'll understand why we know later on, But we know that those are legal AVL trees. There's no problems in subtree A, B, or C, so let's not worry about the details. Let's just say we have a subtree here. We're not going to break it up or mess with it or whatever. We'll just have a subtree, and we'll just kind of deal with it as one unit because there's no need to look at the details. We're not going to be messing with it at all. We kind of will be in a moment, but the idea is that's why we don't need to look at any more detail of those. We'll just sort of deal with that subtree as a unit. The stuff we're concerned about in our example is going to be the stuff I've actually shown. So this has height h plus 1 because the maximum of those two plus 1 is h plus 1. The maximum of those two plus 1 is h plus 2, so that height is h plus 2. And if we want to get into balances, the balance here is 0 because the subtrees are equal. The left subtree is one more than the right, so the balance here is negative 1. And there's a legal AVL tree to start out with. So once we've done this, now let's imagine we do an insertion. And let's say whatever node we happen to be inserting, it's less than K2 and less than K1, so we'd be inserting it into subtree A. And we're not really going to be concerned about the details of how this is chained or whether it's, some left part of A or the right part of A. We don't care about that. What we will care about is, let's assume that the insertion into A ends up being a node that increases the height of subtree A. That is, however A is set up, this new node is inserted as a child of something else, just like every node would be. That used to be a null pointer, now it points to some new node. And that new node is the first node of that depth in tree A. So again, we're saying we've covered up a lot of details. There's a bunch of nodes in subtree A. We're not looking at them. We're just saying, let's assume for the sake of argument, whatever that node happened to be that we inserted, it sort of broke this bottom plane of the tree. We said everything else used to be of depth h. Now this is of depth h plus 1. It's a little bit deeper than the other nodes because of where it's being inserted. Which would mean that now the entire height of subtree A becomes h plus 1 because we've got this whole, it's the height h plus then one more level down for this new node. And so that means the path to a deepest leaf, counting from the root, is now one larger than it used to be because now you have a leaf that's one level deeper than some of the others used to be. And that means now that this height changes to h plus 2, and the balance there is negative 1. And this height changes to h plus 3, and the balance there is now negative 2. So we go up, and we're saying here that there's a chain reaction to this insertion. Even if we assume, we're saying, assume A is okay. Nothing's gone wrong with A. There's been some height and balance changes, but let's assume everything is legal inside A. And everything's legal at K1 as well. The height of K1 increases because one of its subtree heights has increased, and therefore now the maximum of the subtree heights is larger than it used to be. And then when you add 1 to that, that's going to be larger than it used to be as well. And likewise, the balance of K1 has changed, but negative 1 is a perfectly reasonable balance. So there's nothing wrong with K1 either, but at K2, we have a problem where the balance at K2 is going to be illegal now. Because now the height of C is h, the height of K1, which is the root of that whole subtree on the left, is h plus 2, and h minus quantity h plus 2 is negative 2. So we need to fix K2. And this is where the rotation comes in. And we're going to come back to this picture in a moment. The idea of a rotation is going to be here that we have simply picturing things like this. Picture it as sort of a weight or a barbell, where you sort of grab the kind of a big weight by the handle there, and then lift the weight up and down to build muscle. Picture it like that, where it's sort of you can sort of take your hand and grip. Again, lousy art. No one has a wrist that thin, but anyway, you can take your hand and sort of grip that sort of bar between two weights and twist it. Kind of give it a twist and have K1 here like this and K2 like this. It's a lot easier to do this in class when everyone can see me. All you can see is my drawings. So I'm trying to illustrate this concept to you now. But anyway, that's the idea. You're sort of taking this, I guess you can't see my hands, and twisting like that. That's going to be the concept behind a rotation. To grab the tree between the root and one of its children and give it a twist. Rotate it. And these subtrees will come along for the ride in a sense because we'll have subtrees attached there. 3 of them. The fourth one, of course, is the K2's left subtree, and that's K1 itself. but the K1 will have 2 subtrees, K2 has room for 1 more subtree, and they need to be, these are the 3 subtree positions you have there available to you. So you can imagine then that whatever used to be here as the left child of K1 can still be the left child of K1, and whatever used to be here as the right child of K2 can still be here as the right child of K2. And this is going to be sort of the subtree B in our picture that has to move over. Divide this here. So the left child of K1, the right child of K2, those can stay in the same place. The right child of K1 has to detach because now K1's losing K2 is now going to be the right child of K1, so there's not an extra spot. And K2 now, which formerly had a child, K1, now doesn't, so it'll have room in its left pointer, and B can be attached there. And everything will work okay, because any subtree that's in this position, everything here was greater than K1, because it's on the right of K1, and yes, yet it was less than K2, because it's in the whole left child of K2. Greater than K1, less than K2. Same thing here. It's less than K2, because it's on the left side, but since it's on the whole overall right side of K1, it's greater than K1. So the ordering principle for a binary search tree is maintained when we deal with this because of how this is set up. This subtree here is greater than K1, less than K2. When we do the rotational twist, the position that's opened up there is a position indicating that everything here is greater than K1, less than K2. So everything works okay. And so that will be the idea of a rotation. The idea here will be that we'll give the subtree sort of a twist and move this middle subtree over, and everything will be okay. So we're taking here and giving this a twist. K1, K2. The subtree A, the left child of K1, stays the same. So this whole thing became H plus 1. The subtree, right subtree of K2, which was C, can stay the same. And the right subtree of K1 moves over to become the left subtree of K2. Let me again draw a line, vertical line down the center here, though it might be easier to read on your slide. The height here is H plus 1. The balance is 0, because both of these are equal, and they're H. And here, K2's height is H plus 1. The height of subtree A is H plus 1. So the balance there will be 0, and the height is H plus 2. And then whatever used to point to K2 now should point to K1. So obviously you'll be passing in this pointer by reference for the same reason we passed it by reference with the insert and remove for binary search trees. I want to be able to change what this pointer points to from the node above it. But that's the idea. The single rotation has moved K1 up to the root and K2 down to be the right child of the root, as we saw in the previous slide. A and C stayed in the same places. A is still the left child of K1, C is still the right child of K2, and B detached and moved across to become the left child of K2. And that has fixed things. This rotation has changed a balanced -2 node to a balanced 0 node, which is what we wanted. We wanted to get rid of that -2 because since the subtree heights have to differ by at most 1, the only legal balances on a node are 0, +1, and -1. We're not allowed to have balances of plus or -2. And so now what you're sort of getting, in addition to seeing the single right rotation, is a vague hint of where we apply rotations. We apply rotations to nodes that after our insertion or removal now have a balance of plus or -2. When we encounter a node that has a balance of plus or -2, we will then say, well, this is a node that needs to be repaired with a rotation. We will apply a rotation at that point, and it'll fix that node. As we saw here, this node now, the root of this subtree is now a balanced 0 node and not a balanced -2 node. And we didn't cause any other problems anywhere else either. Another way to think about this is to say, if this is my original tree, I can say, well, since K1 is going to rotate upwards to become the root, imagine putting your finger at K1 and imagine these other subtrees are attached as if they were attached by strings. So I can put my finger on K1 and then sort of just let gravity do its thing and let everything else sort of drop. So I'd have here subtree A and subtree B, and then K2 would sort of flop down as well. So if everything was attached on strings and I'm holding everything up with my finger with K1, then everything sort of flops down. A hangs from K1, B hangs from K1, and K2 then gets taken over by gravity and kind of gets pulled down, and it hangs off K1 as well. So you can picture it like that. And then, of course, you're not allowed to have 3 children on K1, so you have to detach one, and so then we say, well, I will now break this off and attach this here. So that's another way of viewing this in your mind. Instead of trying to do kind of the previous picture where you're twisting things, picture yourself putting your finger on what will become the new root, letting everything sort of flop down, and once you've done that, you can take the middle subtree and attach it to the open location. So that's the idea of a single right rotation. We're rotating to the right. The left child, therefore, becomes the root. Everything is rotating upwards this way. And as you saw in the previous slide, or I can actually put it back. As you saw in this slide, it does indeed fix the problem here at the root of that subtree. So what we're going to pick up tomorrow, where I'm going to leave you off at this point, is to say what you should think about here is how exactly this would be coded. Given that you have a reference to this pointer, try and write code to go from this state to this state in general. So you don't want to call them to read the node containing K2 or whatever, but you have some pointer P or temp or whatever that this is called. How do you code to go from this situation to this one? And we will pick up there tomorrow and then talk about the double rotation and sort of finish off a very general discussion of things. That is it for now. I will see you next lecture. Take care.